Hello students. In this video, let us discuss about Lenz Law. Before discussing about Lenz Law, once let us recall about Faraday's laws which we completed in my last video. Right? So the Faraday's first law says that whenever there is a change in a flux linked with the circuit, an induced EMF is set up in the circuit. This we call it as Faraday's first law. So whenever magnetic flux linked with coil changes, an induced EMF is established or is generated in the coil. This we call it as Faraday's first law. Right? Now next, Faraday's second law says that the magnitude of induced EMF is equal to negative rate of change of magnetic flux. Right? This is Faraday's second law. If N turns are present, then induced EMF is written as minus N d pi b, b for magnetic flux, magnetic field. So d pi b is magnetic flux. We will write it as minus N d pi by dt. Right? So these are the Faraday's first and second law. Now the question is, what is the direction of current? Now the question is, what is the direction of current, induced current. To find this direction only, Lenz proposed a law. As it is proposed by Lenz, we call it as Lenz law. So now this negative sign in the equation gives the direction of current. Okay. Now to know the direction of current, let us discuss about one experiment. Okay. So first, you take a circular coil. Okay. Take a circular coil. Now take a bar magnet with its north pole facing towards the coil. Okay. Bar magnet with its north pole. What you did? You took a bar magnet with its north pole facing the coil. As usual, this bar magnet will produce magnetic field. Okay? It produces magnetic field. Just you move bar magnet towards the coil. As bar magnet approaches nearer to the coil, the flux lines of the bar magnet starts linking with the coil. The flux lines. Okay? The flux lines from the bar magnet starts intersecting the coil. As you bring bar magnet closer and closer to the coil, the flux linkage with the coil increases. So, as bar magnet comes closer and closer to the coil, what is happening? Flux linkage is increasing. Now, due to this, what happens? This change in flux linked with the circuit produces induced EMF in the coil. This is nothing but Faraday's law. This flux linkage, whenever there is change in flux linkage, here change in flux linkage means as you bring the bar magnet closer and closer, the linkage of flux with the coil is going on increasing. So that change in flux linked with the coil produces induced EMF. Induced EMF means nothing but an induced current is associated with it. Okay, induced EMF means nothing but an induced current is associated with it. Means when you bring the bar magnet closer to the coil, the flux linkage increases. So this increase in flux linkage produces or generates or establishes induced EMF in the coil. And induced EMF is nothing but an induced current is associated. So in such a way, the magnetic field change produces induced current in the coil. Okay. Now, when bar magnet, the next one is when bar magnet is still closer to the coil. When it comes still closer to the coil, it starts repelling. This coil repels bar magnet. So coil is repelling the bar magnet means what happens? We are bringing north pole. We are bringing north pole towards the coil, no? Means here what can we say? Here I said repelling. Repelling means the coil must have turned into the north pole, no? So when it repels, when coil converts into the north pole only, bar magnet's north pole will be repelled. Means the coil has converted into north pole. So coil is converted into north pole means what? Can you guess the direction of current? In my starting videos we discussed coil converted into north pole means the current is flowing, induced current is flowing in anti-clockwise direction in coil. Means in this direction, current is in anti-clockwise direction. So if current flows in anti-clockwise direction, the coil turns into the north pole and the north pole of the coil starts repelling the north pole of the bar magnet. Right? Now similar experiment, let us see. This is when bar magnet is pushed towards the coil. Pushed towards the coil. The similar experiment, let us see when bar magnet is pushed away from coil. Away from coil. So now, as usual, north pole is facing the coil. Okay. Now what happens? Now, so flux linkage. Now bar magnet is pulled away from the coil. It is moving away from the coil. When it is moving away from the coil, what happens? When bar magnet moves away from coil, what is happening? The flux linked with coil decreases. Am I right or wrong? Now here flux is increasing as the bar magnet is coming. The magnetic effect on coil is increasing. Here it is moving away means the flux linkage is decreasing, no? Right? The flux linkage is decreasing. Now, when it goes to certain extent, the coil starts attracting the bar magnet. Okay? when this bar magnet moves up to certain distance, the coil starts attracting the bar magnet. The coil is attracting the bar magnet means what? The coil is converted into south pole. Right? Attraction will be between the north pole of the bar magnet and south pole of the coil. Means the coil has converted into south pole. So how the coil is converted into the south pole? We can say that when bar magnet is moving away from the coil, the direction of current has changed. Direction of current has changed. And this direction of current will be in a clockwise direction. Okay? This will be in a clockwise direction. So when current flows in clockwise direction, the coil converts into south pole. So now there will be attraction between the bar magnet and the coil. Okay. Now the direction of current totally depends upon the direction of bar magnet. Movement of bar magnet. The exact word, the movement of bar magnet. So when the bar magnet is moving towards the coil, the induced current generated will be in anti-clockwise direction and coil converts into the north pole, and there will be repulsion between the north pole coil and north of bar magnet. And when bar magnet is pulled or pushed away from the coil, the induced current changes the direction. It starts flowing in clockwise direction, and due to this clockwise direction of current, coil converts into south pole. Right? Now there will be attraction between the north pole of the bar magnet and south pole of a coil. Right? The coil acting as a south pole. So now here what is happening? When the flux linkage is increasing. Here what is happening? Flux linkage is increasing. The induced current is trying to decrease it. Repelling means what? It is trying to decrease the flux linkage. And here when flux linkage is decreasing, flux linkage is decreasing, what is happening? The induced current is trying to increase the flux. Increase the flux means it is attracting the bar magnet towards it, means nothing but it is trying to increase the flux, no? So in general, what can we say? Whenever there is increase or decrease in magnetic flux linked with circuit, induced current opposes the changes in increase or decrease of flux. If it increase, it tries to decrease. If it decrease, it tries to increase. So now the statement of Lenz law. How we can write the statement of Lenz law? It states that the direction of induced current is such that it opposes the cause which produced it. Can I say this? What is that cause which produced induced current? Nothing but the magnetic flux. Due to magnetic flux linkage only, either increase or decrease only, the induced EMF has generated in the coil. And after the induced current has formed, the direction will be in such a way that it is trying to increase or decrease the flux. That is, if flux is trying to increase, it tries to decrease. If flux is decreasing, the induced current tries to increase the flux by attracting the bar magnet. So the direction of induced current will be opposite to the increase or decrease of flux linkage with the coil. So this negative sign indicates that particular direction of current itself only. So this is all about the Lenz law. In next video, let us know whether the law of conservation of energy is valid or not. Thank you.